oxidation of the alcohols. So in this oxidation of the alcohols, with what type of the reagents? In previous sessions we have discussed the so many oxidizing agents, but in today's session we are going to introduce oxidizing agent, that is periodic acid, which is HiO4, or else instead of the periodic acid you can use the sodium periodate, means it's salt, sodium periodate. So its formula is NaIO4, or else you can use the potassium periodate, KiO4, or else you can use the lead tetraacetate, lead tetraacetate, PbCHCOO taken 4. So the use of these reagents means they will have the same chemical behavior. These 4 oxidizing agents having the same chemical behavior towards the alcohols. Okay, so let us see how these oxidizing agents works towards the alcohol. Generally these oxidizing agents do not react with the single OH group contained alcohols. They react with the diols. In this sense, these oxidizing agents, particularly if 1,2 diols are there, then they react with the 1,2 diols. Let us see the 1,2 diols category, how they react with the 1,2 diols. A mechanism I am not explaining, which is not important for you. So in 1,2 diols means this 1,2, when these numbers are mentioned, it means that the OH groups are placed on the adjacent carbon atoms. So that these are also called as the vicinal diols. So 2 OH groups are placed on the adjacent carbon atoms. If any alternative carbon atom is there, then they don't react again. So OH group must be placed on the adjacent carbon atom. So the condition is OH groups must be placed on adjacent carbon atoms. These reagents are so important and easy also. Let us see how they work, how they oxidize, and how the functional groups are converting. See, in any alcohol, OH group is there, means in this 1,2 diol, OH bearing carbon atom, hydroxy bearing carbon atom, if it is having at least one hydrogen, this shall be converted to the aldehyde group. You must remember this one. Means the other connection is there again like this. Only this particular part, OH bearing carbon atom with at least one hydrogen, shall be converted to the CHO part. Then OH bearing carbon atom, see now I am taking carbon atom having no hydrogens, means this particular group. Here this one will be oxidized to the keto group. Okay, next. This is about the 1,2 diols. Here 1,2 diols means one is the carbon with OH, hydroxy carbon with OH hydrogen, and another one is the hydroxy bearing carbon with no hydrogens. Like a secondary alcohol, this is like a primary alcohol. We should not use those words, but we can, to some extent, let us use. So the groups will be like this. Then apart from this, there is 2 more categories regarding the not only 1,2 diols, even they oxidize the alpha hydroxy carbonyl groups. Alpha hydroxy carbonyl group means here If any carbonyl group is there, like aldehyde is there, that shall be converted to the carboxylic acid. Okay, I'll give you some examples so that you can understand it clearly. And if any keto group is there, that keto group one side with some carbon part, the other side with some hydroxy part is there, then this shall be converted to the carboxylic acid, like this one, COOH. Here it will be disconnected. And the same keto group, you must observe this category is this is very important. You see both these sides. If a keto group is placed between the two carbon atoms having the OH group, in such cases, this particular keto group shall be converted to the carbon dioxide. Okay, so this is the one category. So I'll repeat this one. I'll show you once again. In the case of the 1,2 diols, two OH groups are placed on the adjacent carbon atoms. In that, if one carbon atom is having the hydrogen, then it will be this only carbon will be converted to the aldehyde part. And the carbon that is not having the hydrogen but carbon links are there, then that shall be converted to the ketone. If it is also having the both the carbon atom, then this part also will be converted to the ketone. Okay, so and in alpha hydroxy carbonyl compounds means aldehydes and ketones. See here, CHO keto group is there. That keto group is placed between the two carbon atoms. In that one carbon atom is having the OH group, the other one is not having the OH group. Then this CO group shall be converted to the carboxylic acid. But if these sides OH groups are there, then CO group shall be converted to the carbon dioxide. And the last one is, I will reveal the trick at the end. First of all, you see alpha amino hydroxy groups also behave as hydroxy group. You treat this amino group NH2 group also just like hydroxy group. So how the hydroxy groups are being converted here, like aldehydes and ketones, the same thing you have to follow over here also. So now let us see here how the examples. Let us see some examples. So in example reactions, what is happening basically? Basically means I'll take one example here. CH2OH and this is CH2OH, ethylene glycol. So when you subject this particular molecule with HiO4, NaIO4, KiO4, lead tetraestate, all these reagents basically whenever two OH groups are placed on the adjacent carbon atoms, immediately they break the bond between that carbon atoms. And if the carbon atom is having at least one hydrogen, that shall be converted to the aldehyde. And here also one hydrogen atom is there, so that it is also shall be converted to the aldehyde. Now let us see here another example. CH3, CH3, OH, OH, CH3. Here hydrogen I placed it. Now use NaIO4. Any reagents can be used. So what is the basic in property of these reagents? They break the bond between the two OH bearing carbon atoms. So they break the bond here. So first of all you break the bond and you see whether the carbon atoms are having the hydrogen or not. Here carbon atom is not having the hydrogen. So this particular part shall be converted to the ketone. And this particular part, if you see here hydrogen is there, so this shall be converted to the aldehyde. Okay, now let us see their respective products. Anyhow, we have broken this bond, so this carbon atom will be converted to the keto group. Remaining CH3 groups are as it is. So CH3, C double bond O, CH3, acetone plus here one hydrogen is there. So this particular group will be oxidized to the aldehyde. CH3 group remains as it is here. So this is CH3, CHO. Hope you understood. Now let us take one more example. Third one, CH3. You take all methyl groups now. Means OH bearing carbon atoms are not at all having any hydrogen, but only OH groups are present. Now you take KiO4. Just I am taking different examples, different reagent examples. So break the bond because two OH groups are there. Again, both are carbon atoms where we are breaking the bond, that carbon atoms are not having any hydrogen. So convert them into the keto group. So here CH3, C double bond O, CH3, this first part, and second part also will give the same molecule. CH3, C double bond O, CH3. Okay. Now let's take some cyclic example. And this is the fourth example, I hope. Yeah, it is the fourth example. So in this fourth example, you see here OH group is present, and you take HiO4, or you can take the lead tetraestate also. So it will break the bond here. 1 minute. So here hydrogen is present, and here also hydrogen is present. So this shall be converted to the aldehyde, this also shall be converted to the aldehyde. CHO group, and it is also CHO group. Now let us try to place OH group, take lead tetraestate Pb, CH3COO taken 4. Now again you break the bond over here, and this part is having the methyl group. This is the methyl group. So this carbon atom where we are discussing, this particular carbon atom shall be converted to the keto group. This is the keto group, and this being having hydrogen shall be converted to the aldehyde, so that the particular molecule, final molecule will be, this is the keto group, here CH3 group, and this shall be this is the carbon, here hydrogen, yeah, CHO. This is the molecule. So in this way you have to understand. So this is about only 1,2 diols. We have taken only 1,2 diols examples. Now let us take these examples also. What about when keto group is there, how it will be breaking, and what about the amino groups, everything. So let us take these examples also. So in these examples now, first example of the aldehyde and ketone category, that is alpha hydroxy carbonyl compounds. So how they react towards this HiO4 or NaO4, these oxidizing agents. So let us take here CH3, because this is so important in glucose biomolecules chapter. CH2OH. Now you just use the HiO4. So what is the property of HiO4? Wherever the keto OH groups are in the adjacent carbon atoms, or two OH groups on the adjacent carbon atoms, or NH2 and OH groups are in the adjacent carbon atom, then it breaks the bond. So it breaks the bond here, and this OH contained carbon atom is having at least one hydrogen, so this shall be converted to the aldehyde plus, and here this is connected to the CH3 group, means carbon having no hydrogen, so this shall be converted to the carboxylic acid, CH3COOH. Now let us take one more molecule. What happens instead of this methyl group? What happens if aldehyde group is there? Let us take the aldehyde. CH2OH. Use the HiO4. Again, this shall be converted. This particular part shall be converted to the aldehyde, as it is having the carbon with hydrogen, and basically these two are adjacent groups. See, if these two are at least two OH groups, or OH group and keto group or OH group and aldehyde group or amino group, if they are not on the adjacent position, then no oxidation reaction takes place. And being an aldehyde, this one having no carbon this side, so this shall be converted to the carboxylic acid. Okay, this is aldehyde group. Aldehyde group will be converted to the carboxylic acid. Now, so this is carboxylic acid HCOOH, and this shall be converted to the aldehyde. Now, generally doubt arises, what happens if the groups are like this, if the molecules are like this? In the sense, let us take CH2OH, C double bond O, CH2OH. So when this is subjected to the HiO4, then what we have to do? We have to break the bond between these two carbon atoms and between these two carbon atoms. So this CO group will be converted to the carbon dioxide because both the sides we are breaking the bond. Okay. So first of all, I'll write this one. This is having the hydrogen with OH group, aldehyde, plus this shall be converted to the carbon dioxide, and this shall be converted again to the aldehyde. Now again let us modify this molecule, third molecule, CH3, CH, OH, C double bond O, CH2, OH. So HiO4. Again what to do here? These are all in the adjacent position. So break the bond here. Again this shall be converted to the aldehyde. This will be converted to the carbon dioxide. And here there is no other particular methyl group, but this is having the hydrogen with OH group, so that this shall be converted to the aldehyde. CH3, CHO. Okay. And in this course particularly, I forgot one important example, that is what happens if the molecule is like this. Use HiO4 now. So we need to break the bond here and here. Again this will be aldehyde, this will be aldehyde. That is very clear. Aldehyde plus this is also aldehyde. Then what about the course of this particular reaction? This is breaking on both the sides. Actually it has to be converted to the aldehyde, but the aldehyde will be oxidized to the carboxylic acid, so that it gives the formic acid. So any OH bearing carbon atom, if it is broken on the both the sides, will be converted to the carboxylic acid. If it is broken on the only one side with hydrogen, shall be converted to the aldehyde. Broken on the only one side with no hydrogen, shall be converted to the keto group. So I'll write the points here. You just note down those points. Note. But condition is OH groups must be on the adjacent carbon atoms. Any OH bearing carbon atom broken on both the sides will be oxidized to carboxylic acid. This is the first point. Second point, any OH bearing carbon atom broken on one side and having hydrogen will be oxidized to aldehyde. And any OH bearing carbon atom broken on one side and having no hydrogen will be oxidized to keto group. I think this is clear. And next, here only I will write one more point also. Any C double bond O group broken bond, actually bond, carbon bond is broken on only one side, will be oxidized to carboxylic acid. And any CO group is broken on both the sides, will be oxidized to carbon dioxide. So these are the important points to understand or to remember in this particular oxidizing part. Now let us see alpha amino groups. What happens if alpha amino groups are also present? As I said, alpha amino group behave as hydroxyl group and gives same results as in the case of vicinal diol. Now let's see some examples of this category also. CH3, CH, NH2, CH, OH, CH3. Subject it with the HiO4 or NaIO4, sodium periodate. So just treat this one also like OH group, so that this is aldehyde, this is aldehyde. So break the bond here. CH3 CHO plus CH3 CHO. So the molecules are like this, the products. Now let us take this some application, lengthy products, because in biomolecules you might have learned these examples. So I will take those examples over here now. We just take the glucose molecule. So there are 4 CHOH groups, and the other end CH2OH group, and here CHO group. Now you subject with the HiO4. To disconnect one link you need one HiO4. So here how many bonds you are going to disconnect? 1, 2, 3, 4, 5. So that how many HiO4 molecules you need over here? 5 HiO4, 5 moles. So they may ask the question, how many moles are required? 5 moles of HiO4. And in this particular case, let us see how the molecules are coming. First of all, this particular part, carbon, because these are all OH groups, and here aldehyde group is there. So OH groups on the adjacent carbon atom, this is having the carbon with hydrogen, and only one side it is broken. So this shall be converted to the aldehyde. And remaining cases, you see OH groups are there, at the same time hydrogen is there, but broken on the both the sides. So all these 1, 2, 3, 4 are converted to the carboxylic acid, and aldehyde group broken on the one side. So this also will be converted to the carboxylic acid. So totally 5 carboxylic acid molecules will get. So 5 HCOOH formic acid molecules, and aldehyde is from here, HCHO formaldehyde. Now let us take this fructose molecule also. CH2OH, C double bond O, CHOH, 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 and last CH2OH. Subject it with the HiO4. Again you need to break 1, 2, 3, 4, 5 bonds, so that 5 HiO4 molecules are required. So when you are breaking these bonds, you have to observe so many things. And here CH2OH group only one side, this is also only one side. So these two molecules gives the aldehyde. So means two molecules of HCHO, formaldehyde. And CO group is broken on the both the sides so that it shall give the carbon dioxide. And these CHOH groups broken on the both the sides, so they will give the carboxylic acid. 1, 2, 3. 3 moles of formic acid will be produced. So in this way, these oxidizing agents actually works. So hope you understand this one, how periodic acid NaIO4 is working. So it is very simple to understand that. Basic thing is these points you need to note down in your notebook. So if you remember these one and one examples are enough, not all the examples. So now I'll give some examples. Please, okay, I'll solve these questions, but we'll give some time, 1 minute time. You just try to solve. Okay, this is also looking good. Let me try this one, how it looks. Black anyhow we can't try. Draw the organic products. Okay, draw the organic products in each of the following reactions. But this blue we cannot use for long time. This black is not required now. Let us change this color to some light color. Okay, let us use this one. I don't know how it looks. Okay, I'll give some questions here. I only will give the answer also, but within 1 minute time you need to solve before I complete this writing of all these questions. PCC, pyridinium chlorochromate, and B compound. CrO3, H2SO4, and H2O. OH group, PDC. I'll write this side. Okay, one more molecule right here. D molecule. So here this is the OH group. Means almost all reducing oxidizing agents, I mean H plus, KMnO4 and heat it. And E example. So before I solve, you try to solve this one. Now only. H plus, K2Cr2O7 and hydrolysis. And F, DMSO, dimethyl sulfoxide. G, MnO2. Please don't wait for me, just to solve it. H, CH2, let us give the big molecule. CH2OH, CHOH, C double bond O, CH2OH, 1, 2, 3, so 3 moles of HiO4 I am giving here. BH, I. Jones reagent. J. HiO4. Now let us solve these questions. We know that these all oxidizing agents except H plus K2Cr2O7 KMnO4, which are the strong oxidizing agents, rest all are weak oxidizing agents. Okay, so they just convert the primary alcohol to the aldehyde, secondary alcohol to the ketone. So let us take here, this is the primary alcohol which shall be converted to the aldehyde. So this particular carbon, 1 2 3 4, 1 2 3 4. So this fourth carbon shall be converted to the aldehyde, this particular carbon. Okay, and B example, Cr2 CrO3, this is called as Jones oxidizing agent, so that here it will convert this particular secondary alcohol to the ketone. And C PDC, again secondary alcohol to the ketone, oxidize that. And let us take this is H plus KMnO4, so this particular one primary alcohol will be oxidized to the carboxylic acid. COOH. Now, so now here this is also H plus K2Cr2O7, but secondary alcohol. H plus KMnO4, K2Cr2O7, CrO3, H2SO4. This one, and this one. These three are the strong oxidizing agents which converts the primary alcohol ultimately the carboxylic acid. But secondary alcohol is only ketone, so that this is also giving the ketone. You please remember those oxidizing agent properties. Dimethyl sulfoxide converts primary alcohol to the aldehyde. MnO2, which is a very good oxidizing agent, whose property is to oxidize the allylic and benzylic OH groups to the keto groups. We have already discussed the MnO2 is a very selective oxidizing agent which oxidizes only allylic and benzylic alcohols to the respective carbonyl compounds. And here 3, so that this shall be converted to the aldehyde, plus this shall be converted to the carboxylic acid, plus this shall be converted to the carbon dioxide, plus this shall be converted to the again aldehyde. Just now we discussed. And Jones oxidizing reagent, secondary alcohol. So secondary alcohol means the ultimate product is ketone, whether you use strong oxidizing agent or a weak oxidizing agent. But you must know Jones reagent is an oxidizing agent, not the reducing agent. Keto group. Now HiO4 is there. Just both H and J are the examples of the breaking bond category. So here you need to break the bond. Here hydrogens are there. So this part shall be converted to the aldehyde. Okay. So this part having no hydrogen but carbon connections are there. So this OH contained carbon means this particular carbon shall be oxidized to the keto group. So these are the answers. Hope you understand. If you have any doubt, please do ask me. I'll wait for 10 seconds. Now let us see one of the important reaction, that is opener oxidation. Opener oxidation is a very simple reaction. It is also one of the important oxidation in which we take secondary alcohol. We take a secondary alcohol. So this secondary alcohol is subjected with a ketone. Usually we take acetone here. Okay, here we take the ketone, and in this particular area we take the aluminum isopropoxide, aluminum tertiary butoxide. Two reagents are there, OCMe3 taken thrice. So the secondary alcohol shall be converted to the ketone. Okay, and interestingly this ketone shall be converted to the secondary alcohol. So this is the example, and here reagent. First of all, I have to discuss about the reagent. Reagent is aluminum tertiary butoxide or aluminum isopropoxide. Okay, so this is the tertiary butoxide, and isopropoxide also I'll show you now. What is the difference between these two reagents? A simple thing, aluminum OCCH3. These CH3 groups 3 are there. 3, again these are 3. Why? Because aluminum valence is 3. So the structure of this reagent is aluminum is connected to the oxygen, next carbon. This carbon is connected to 3 methyl groups every time. So like this. You can see this particular area, this is a tertiary butoxide. Like that, how many are there? 3 are there. So aluminum tertiary butoxide, tertiary butyl group this is, and aluminum isopropoxide group. A very simple, similar reagent, and you cannot find out the major difference. O, here CH will be there, and the CH3 groups only 2 will be there, and totally 3. Means instead of one methyl group here, we put one hydrogen. So I'll write that structure also here. Aluminum, oxygen, carbon with hydrogen, methyl group and methyl group. Oxygen, carbon, hydrogen, methyl group and methyl group. This isopropoxide part. Okay, so in this reagent we use the aluminum tertiary butoxide or aluminum isopropoxide, and commonly used ketones. Whatever the ketone here we are using, usually these ketones are either acetone or we use the cyclohexanone. Okay, so let us take the major thing is opener oxidation is only for the secondary alcohols, not for the primary alcohols. If you want to oxidize the primary alcohols to the aldehyde, then you should not use the uh, this one acetone, but you have to use the parabenzoquinone. That also I'll write here. Note point. So note, primary alcohol may also be oxidized to aldehyde If acetone is replaced by parabenzoquinone. Okay, so now let us take some examples how to understand this secondary alcohol and all these examples. And it is a here one more thing I have to inform you, that is it is an oxidation reaction, open or oxidation reaction. Actually, it is a reversible reaction. The reverse reaction is a reduction reaction because we are oxidizing secondary alcohol to the ketone. And the reverse reaction also, same oxidizing agent acts as the reducing agent. That reaction is called the Merwin-Pondorf-Verley reduction, MPV reduction, that we shall discuss in the coming examples. Aldehydes, ketones, carboxylic acids. So now let us take some examples. You just take one particular alcohol. I'll take some secondary alcohol. I'll take methyl group directly so that it will not confuse you. CH3, CH, OH, CH3. This is in your NCERT textbook. This example. This is called the isopropyl alcohol. So this isopropyl alcohol, when subjected with the aluminum tertiary butoxide, generally we use aluminum tertiary butoxide for oxidation, aluminum isopropoxide for the reduction, and we use CH3, C double bond O, CH3 acetone. And interestingly, this will be converted to the keto group. I have to make a difference between these two now. So I'll do one thing, that I'll take here, 1 minute, CH3, CH2. Otherwise, you get confused whether this acetone is coming here or not. So this shall be oxidized to the CH3, CH2, C double bond O, CH3. So this is oxidized to the ketone, and this shall be reduced to the alcohol, CH3, CH, OH, CH3. So this is oxidized, this is reduced. Now let us take the second example. Very beautiful examples are there, and I will give the MnO2 also, how it is connected here, what is the resemblance. So I will take this one secondary alcohol, same aluminum tertiary butoxide, C, Me3 taken thrice, acetone, CH3, C double bond O, CH3. Acetone I will take so that this shall be converted to the ketone group. Interestingly, you might have observed one thing, that sometimes this ketone they will give here, this secondary alcohol they will give here. So you should not get confused. This catalyst they will give here, like this. Both are same, like CH3, C double bond O, CH3. Why? Because this shall be converted to the alcohol now. This is important thing you have to notice. So Al, OC, they will confuse you like this only. Now here they will give the alcohol. So they may ask the product. Product means this product only. You have to write down both the products. Single product they don't ask. If they ask only this one, secondary alcohol, without this product, then this is the answer. Secondary alcohol is the answer. Both the products they don't mention. Okay. Next, let us see here one more, some more examples. Fourth one. ALOC Me3 taken thrice, CH3 C double bond O CH3. So this shall be secondary alcohol, whether it is allylic alcohol, benzylic alcohol, whatever it may be, it must be a secondary alcohol. So secondary alcohol has to be oxidized to the ketone. Okay, and the same one specifically, if you want to convert the same compound to this one, we use one more oxidizing agent. You know that oxidizing agent MnO2, which specifically oxidizes the allylic alcohol to the respective carbonyl compounds. Let us take another example. This is a molecule where again I am using aluminum tertiary bit oxide. Again, this is an allylic alcohol. So it has to be converted to the aldehyde part. Here we should not use, because it's a primary alcohol, no? So here we should not use this one. So I will mention another, that is quinone, benzoquinone, para-benzoquinone. So like this opener oxidation is there. So opener oxidation main importance is to convert the secondary alcohol to the ketone using this aluminum tertiary bit oxide with acetone. Okay, here you can use the cyclohexanone also. So let us see one of the most important reaction, that is esterification reaction. This is also known as the Fischer esterification reaction. This reaction is so important because they'll ask the question based on the oxygen presence. Which oxygen is left, which oxygen is still present. So in this particular Fischer esterification reaction, carboxylic acid, we take one carboxylic acid, reacts with the alcohol, in the presence of this one is this is a reversible reaction. In the presence of the acid in the sense, generally we take the H2SO4, then we get the ester plus H2O molecule. And the question is about within this sorry, here I have written wrong thing. Carboxylic acid is written ester. Okay, so in this particular thing, the question is about this oxygen, whether this oxygen is from alcohol or carboxylic acid, and this oxygen, whether this oxygen is from again this C double bond O group or another oxygen is came and now acting as like a C double bond O group. About this oxygen, whether this oxygen is from this oxygen, this oxygen, this oxygen, or this oxygen. Okay, so now for that we need to see the mechanism. Initially H2SO4 step 1, we know that it is a reversible reaction. Dissociation of H2SO4 is a reversible, dissociates into H plus and HSO4 minus. So this H plus and HSO4 minus, H plus is provided here Now we take the carboxylic acid. Okay. So when this carboxylic acid is with the H plus of the H2SO4, the lone pair of electrons present over the keto group, oxygen of the keto group, not the oxygen of the hydroxy group. So they attract this H plus ion because here pi electrons are there, so it is more localized. So we get RC double bond O hydrogen plus oxygen and hydrogen. Now alcohol comes into the work. So alcohol means I'll write like this, R dash. The lone pair of electron, this is a very key step. You must remember this one. And this is a slow step also. Attacking of the nucleophile. So here this attacks on this carbon. The reason is oxygen is getting the positive charge. So these electrons will be shifted more towards the oxygen. So the carbon is left with the no charge, that is positive charge. So that these electrons can easily attack over here. So that is a nucleophilic attack. Nucleophilic is a slow reaction. It is a reversible reaction. Most of these reactions are, all reactions are reversible reactions in the esterification reaction. So now, when it attacks, these pi electrons will shift over there. Hydrogen, oxygen, R dash, hydrogen, O, H. So see carefully. This is with a positive charge now. Okay. So what this oxygen will do, it will withdraw the electrons from the oxygen hydrogen bond. Then H plus ion has to come out. That H plus ion obviously will be attracted immediately by this lone pair of electrons of the OH group oxygen, not this oxygen, both are there. Okay, so it looks like that because two OH groups are there, immediately one H2O molecule has to be removed. That H2O molecule removal will be like this. So the lone pair of electrons of this OH group oxygen attacks over this H plus ion. So finally what happens, 1 minute, the compound will be like this, OH, here now RO, okay. So now here oxygen with two hydrogens. This is also a reversible reaction. And afterwards, now the lone pair of electrons of this one attacks over here and this H2O will be removed. Now if you use this one is oxygen 18, understand, oxygen 18 isotope. So this shall be the oxygen 18, this shall be the oxygen 18, this shall be the oxygen 18, and this shall be the oxygen 18. So the oxygen present in the H2O molecule is from the OH group of the carboxylic acid. Okay. And next, this star alcohol oxygen, star alcohol oxygen. So it remains as it is. Now we will write the molecule R. This is also reversible reaction. R C double bond O H. This is the plus. Okay. Here oxygen. This is the R dash. I forgot to mention over here R dash. So H2 molecule anyhow left behind. So now oxygen with a positive charge is unstable, and I will mention this one as a star oxygen, and later this oxygen hydrogen bond electrons will be completely shifted over to the oxygen, and finally H plus ion will be removed. Okay, so now RC double bond O R dash, and here alcohol retains its oxygen. Carbonyl oxygen of the carboxylic acid also present in the ester. Then from where this oxygen is left means OH group. So I will write the molecule like this. One simple example you can understand very clearly. So overall reaction is, you please see very carefully, RC double bond OH plus HO R dash H2SO4 Now you need to remove the water molecule during the esterification. So in that water molecule, OH from the carboxylic acid and hydrogen from the alcohol. So this shall be removed as the H2O. Okay. So afterwards, R, C double bond O, O, R dash. So carbonyl oxygen is not disturbed. Oxygen of the alcohol also not disturbed. Only OH group from the carboxylic acid and hydrogen from the alcohol is removed. Why? Because people usually think that carboxylic acid is an acid, so that it gives the H plus N. So this H plus N, this OH will be removed, so that oxygen, they say that in ester the COR oxygen is from the carboxylic acid. They may think like that, but it is not correct. But the true thing is this one. Okay. And what are the required conditions? Because this reaction is a reversible reaction, what are the required conditions for the carry out of the forward reaction? Because this H2O is removed over here, no? So I'll write down this H2O on the product side, so that you can understand clearly, even more clearly. Now this is an equilibrium reaction. So in equilibrium reaction, increasing the concentration of the reactants, decreasing the concentration of the product will be favorable for the forward reaction. Okay. So in this thing, when H2O is removed immediately, it will become unbalanced. To balance the reaction, it will the reaction will be shifted towards the right hand side. Then in reactant side, which reactant has to be increased? That is alcohol, because alcohol is the molecule which is a nucleophile that is involved in the rate determining step, slow step. So the rate of this reaction depends on the concentration of the alcohol. Hence it is a pseudo unimolecular reaction. Esterification is called the pseudo unimolecular reaction, not the bimolecular reaction. So I'll write down the point here. Note, the rate of this reaction, the rate of esterification depends on the concentration of alcohol. So increase the concentration of the alcohol or decreasing the removal of the H2O molecule will shift the reaction towards the product side. So this is the esterification reaction. And I need to explain one more important thing regarding the Fischer esterification reaction, that in most of the textbooks or some of the members, they may say that they may use H plus or OH minus also here. If you use the OH minus, the reaction will not proceed towards the product side. The reason here is, I will tell you, we will take some examples later. First, why? Why? Because if this is the carboxylic acid along with the alcohol and you used the OH minus ion. What is the role of OH minus ion? OH minus ion is a base. Carboxylic acid is an acid. So it reacts with the acid, means it takes the hydrogen from the carboxylate ion. So that what it will do is C double bond OH and OH minus and abstract this proton, and these electrons will be shifted over there. So that what we get is carboxylate ion and H2O molecule is formed. Now this carboxylate ion is having the negative charge, so it is an electron rich part, electron rich group now. And alcohol is also nucleophile, which is having the more electrons. So if you take the alcohol, this is also electron rich group. So one electron rich group cannot attack over the another electron rich group. So that is the reason why in the presence of the OH group, OH minus and hydroxide ion, the esterification reaction will not be carried out, and it is carried out only in the case of the acid. Why? Because the important thing is the acid is attacking over the carbon oxygen, so that it creates the positive charge and makes the carbon positive charge, so that alcohol can easily attack over the partially positive charged carbon atom, which leads for the remaining formation of the esters. This is the ester. So basically Fischer esterification reaction definition is carboxylic acids reacts with the alcohol in the presence of the acid to produce esters, is called as the, this is ester, is called Fischer esterification reaction. Let us see some examples of this category. Very good examples are there. So now let us see some examples. Example number 1, CH3COOH. You know this is acetic acid, and CH3 CH2OH, ethyl alcohol. Whenever esterification reaction is there, you have to mention this double-headed arrow mark with opposite direction. Their heads are pointing in the opposite direction. So that ester has to be formed. CH3, C double bond O, CH2, CH3 plus H2O. Second one is, I will take the benzoic acid now. This is the benzoic acid plus alcohol, methyl alcohol I will take. Star mark, so that here star mark plus H2O. Third one is, dicarboxylic acid. This is oxalic acid. You take the oxalic acid, use the glycol, ethylene glycol. H2SO4, so that hydrogen from the alcohol, loss of 2 water molecules. This is the molecule. Let us take this example also. This is so important example. I'll tell you why this example is so important. H plus. Here two OH groups are there, and carboxylic acid we are using. So between these two OH groups, which OH group is more reactive? That is always primary. So primary alcohol, next secondary alcohol, next tertiary alcohol, because primary alcohol can easily attack over the carboxylic acid as steric hindrance will be very less. CH2O, C double bond O, pH. So alcohol side only oxygen must be connected to the carbon, and carboxylic acid side C double bond O should be present. Now, some cases what happens, intramolecular esterification reaction also takes place. Let us see how the intramolecular esterification reaction takes place. I'll change the color. Intramolecular esterification of gamma and delta hydroxy carboxylic acids form 5 or 6 membered esters. So here I would like to inform you one thing, that cyclic esters are called as the lactones. Cyclic esters are called as the lactones. So what is gamma and delta hydroxy carboxylic acids? I'll introduce that now. One example. So apart from the main functional group carbon, the next carbon is called the alpha carbon. This is beta carbon. This is gamma carbon. Okay. So 1, 2, 3, 4. At least 4 carbon atoms must be there. If 4 carbon atoms are there, one oxygen will come into the ring. So this OH group and this hydrogen from the alcohol. Use H plus ion. So that what happens? This oxygen will come over here, no? So this oxygen shall be connected like this plus H2O. Next, second one is, let me cover the syllabus. Why? Because I didn't take the 3 to 4 days now. I need to cover the portion. I'll take one last example, this one, OH, H2SO4. Now, how this will be removed? OH from the carboxylic acid and hydrogen from the alcohol. They will be removed like this. And which are the, how to say this, whether it is gamma carboxylic acid or delta carboxylic acid. You leave this carbon, next carbon is alpha, this is beta, this is gamma, this is delta. Means 5 carbon atoms with 1 oxygen. It is also coming into the ring, so that becomes the 6-membered ring. So why we call this one as the intramolecular esterification reaction? Because the OH group means carboxylic group, OH group, both are present in the same molecule, within the molecule, and water is removed from the same molecule. Hence it is called the intramolecular. Intra means within the molecular. But in earlier cases, carboxylic acid is from the one molecule and alcohol is from the another molecule. So this is not the intramolecular example. This is simply Fischer esterification reaction. And these are the example of the intramolecular esterification reactions. So I'll give some examples for your homework. Please try to solve these examples. And you please send me the examples also. You are not sending. This is not getting selected. Okay. So draw the product of these reactions. First one is H2SO4. Please note down this immediately. So these are the examples. Please try to send me the answers for these examples. like my video, subscribe the channel if you like my explanation. Thank you, one and all.